hear me well. Welcome to my talk about physics-informed neural network to model COVID-19 infection and hospitalization scenarios. And thank you very much for the opportunity to actually give this presentation. I'll directly start with the structure of this talk. So I'm firstly going to explain our ideas and motivation for this work. Then I will talk about the so-called SVIHDR model that are further steps and also implementations built upon. Afterwards, I will give an overview of the methods we used and the procedure, substantially including physics-informed neural network. And subsequently, the so-called non-standard finite difference scheme and long short-term memory techniques will briefly be explained because they will be used as well. And in the results section, the results section is subdivided into parameter identification part via the PIN, meaning physics-informed neural network, a validation part, and scenario generation or forecast part. Okay. Our motivation for this work. Our initial idea was to make use of a data-driven method, in this case, the physics-informed neural network, to obtain the parameters of a model that inherits transition and transmission dynamics and parameters reflecting the effects of the coronavirus pandemic within a selected population. Before that, we used numerical approaches of minimizing the error between reported data, for example, infection number data and numerically developed data points, given a reported initial data set, and obtaining optimized model parameters that way. Now, the PIN approach gave us the quite unique possibility to include the system of ordinary differential equations, which describes our transition and transmission dynamics, into the computation of the loss function of the neural network. And both the numerical and also the data-driven techniques we use here were applied to create future pandemic scenarios, meaning they were not only used for parameter identification or estimation. Regarding the numerical technique, this was performed also in my master thesis, where Rowan-Kutta scheme and the non-standard finite difference scheme were applied to develop the model over several points in time. And also we did that in our recently published paper on a non-standard finite difference scheme for a certain compartment model to predict COVID-19 dynamics, where we made forecasts and analyzed them as well. Now, the benefits of a PIN, in some words, are that we can combine the potential of a data-driven neural network with mathematical models based on physical laws as differential equations in our case. And of course, the PIN can be used for both parameter estimation and prediction. Regarding the loss function, our PIN combines a data and a residual loss in its loss function. So in our case, the data loss is based on German COVID-19 data, which I will give some more details on later. And the residual loss is based on a system of ordinary differential equations corresponding to an extended SIR epidemiological model. In the literature, you can also find the terms epidemiology-informed neural networks or disease-informed neural networks. Epidemiology-informed neural networks can be defined as a type of feed-forward neural network that incorporates epidemiological dynamics, and the disease-informed neural network can be described as a type of physics-informed neural network that can be applied to complex systems describing infectious diseases generally. Yeah, this is just in order to like yeah, put the word PIN in some context maybe. Okay. So the compartments of our model. The usual SIR model that is now known since the media spread it at the beginning of the pandemic already, consists of the three so-called compartments of susceptibles, infected, and recovered individuals. Compartment can be defined as a population group characterized by a certain infection progress. There are several extensions and variations to this model, and only with respect to the COVID-19 pandemic, various scientific papers dealt with different versions using distinct compartments for various purposes to make certain predictions, for example, concerning asymptomatic infections or mutated variants, or there are several things, vaccinations and so on.
Sarah, can I ask you a question? What is the leaky vaccines?
Yeah, I'm going to talk about this.
Oh, okay, sorry. Okay.
So in our model, which is called the SBI-HDR model, we have got 6 compartments. We have got S. These are the susceptibles who have not yet contracted the infection but are able to. We have got the vaccinated people who have a lower probability of getting infected than susceptibles and also lower probability of infecting others. So the term leaky vaccine means that the vaccinated people are not completely protected from from getting infected. This would be the case in the so-called all or nothing vaccine, but they can actually get infected but have this lower probability. That's actually what the term means. Then
it just means that after you are vaccinated, you are not completely immune against COVID-19. And I mean, this is a typical case for a vaccine to be leaky, as we know from the existing COVID-19 vaccines.
Yeah.
Yes, thank you.
Yeah, we can see this, for example, now in the Omicron wave, where so many people get infected, although they are twice or 3 times vaccinated. The infected people have already contracted the infection and can infect others. In our model here, they can be symptomatic, pre-symptomatic, or even asymptomatic. We used data, the official infection numbers published by the Robert Koch Institute, and we also tried to include a dark figure using some kind of factor. And then we've got the hospitalized compartment. It includes infected people that are no mild cases and others, put in hospital, go to hospital. We've got the deceased compartment. It includes those people who died for reasons related to COVID-19, and the recovered compartment of people who have overcome the infection or disease. The total regarded population is abbreviated by the letter N, and usually in compartment models, this number is also constant. It does not have to be the case, but it's often the case. So we also regarded this constant case here. Okay, now we have the transmission rate of our model, which is very important because it determines the transition from the susceptible vaccinated to the infected state or compartment. Firstly, we have a contact rate. It's the average number of all contacts of one individual in the population per unit of time. Then one can include a quarantine rate or isolation rate. It does not necessarily have to be used, but it is sometimes good to describe the effect of intervention measures, state measures. Yeah. Then we have got the so-called effective contact rate. It's the average number of all contacts between a susceptible and an infectious person per unit of time. And the so-called secondary attack rate, it's the average number of acquired secondary infections per unit of time. And what is the most important thing is the transmission risk beta. Yeah, it's normally not computed like this, but it can be, in some literature, it's given as divided by the effective contact rate. But usually in implementations, this is one of the estimated parameters, which is not given as a fixed parameter, but is just estimated by the program, by the method. And of course, we can have all those, like the contact rate, the quarantine rate, and the transmission risk can be time-dependent rates as well. I did that in my thesis, and also we did that in our previous paper on NSFDs. Here in this approach, we firstly used constant values, and now we are also working on this implementation with reasonable time-dependent rates. The time dependence of the transmission risk is, I think, debated as well, because actually the clearest time dependence can be seen with respect to the difference between summer and winter, because we see that the virus seems to be more transmissible in winter than in summer, for example. And the time dependence of the contact and quarantine rate just especially depend on intervention measures. Then we have got kappa, which is the reduction in transmission risk for vaccinated people compared to not vaccinated people. And we get one so-called transmission rate for the infected compartment and one, meaning kappa times theta, for the vaccinated compartment. So yeah, the transmission.
I have a question. So gamma is a constant, right?
Yeah, here it can be a constant parameter. Yes, but we can also,
because like if you go in a lockdown period, for example, which Germany went through many times, or a non-lockdown period, that gamma will change, right?
Yeah, if we have a look at several waves of the pandemic, we've got different states of intervention measures, and this makes sense. That's also why I included time dependence in my master thesis modeling. Genau, but here we just use constant value at first, and you can just estimate it from the data as well. Yeah, and
it depends on the it depends on the time window that you are looking at. If you're just looking on one wave, then it's okay to be constant. But if you look on the last 2 years, then of course it must be time dependent.
Yes, exactly.
Yeah, and our main focus here was the kind of scenario generation for the wave that we are currently in. Yeah. And it's also a kind of task to model this time dependence very reasonably and kind of correctly. So I have to make some thoughts on this. Okay, so in the end, we get a so-called incidence rate by multiplying the transmission rate by S divided by N. This is the so-called standard incidence rate. If we did not divide by n, it would be the so-called bilinear incidence rate, and this one is based on the law of mass action. And yeah, the mass action and the standard incidence rate agree when the total population size is constant. And yeah, we just normalize here. This is also the most common case, I think, to use the standard incidence rate. Okay, we have got transition rates. They describe the transition between different compartments. At first, we have got a vaccination rate. Then we've got a proportion of infected people that are hospitalized. We've got the proportion of hospitalized people that die due to or for reasons related to COVID-19. We have got the average length of the infection period and the average length of the hospitalization period, and thus we can compute our rates. For example, if a proportion of C people transits from the infected to the hospitalized class within TI weeks, then C divided by TI do this within 1 week. So that's how we got these rates. And we've got the hospitalization rate, the recovery rate for infected people that are not hospitalized, the disease-induced mortality rate, and the recovery rate for hospitalized people. And in the next, on the next slide, we can see the actual model. It's visualized in a diagram here. Yeah, the purple arrow symbolizes the transition, and the red dashed one stands for possibility of a transmission emerging from the compartment which the arrow starts at. So yeah, vaccinated people and infected people can infect susceptibles, because vaccinated ones can also maybe get the infection. Yeah, so that's it. And we can find the system of ordinary differential equations like that. It's yeah, it's just based on this compartment model, or it is this compartment model in a way. We have got one rate equation per compartment, and here pluses denote inflow into a compartment and minuses, of course, outflow. Yeah, in the upper left corner, we have got a kind of definition of this whole system where K of T is the compartment sizes at time T, and FP is the equations, and P stands for the parameters of the model, and T is, the time independent variable. So yeah, this is actually the model that we work with and that we put into our implementations. Yeah, we followed the following procedure. Our data originate from the Robert Koch Institute, as I said, and also the German COVID-19 vaccination dashboard. They referred to the calendar week 10 in 2020 to 45 in 2021. So March until November next year. And from these data, we computed 3 fixed parameters, which are given here. And then we used a feed-forward pin to identify beta and kappa. We decided for those 2 parameters to be the most important ones to be estimated or identified, because they were the ones that could not be found in any literature for sure or something. So these were our trainable parameters or trained parameters. Okay, and now using data of the calendar weeks 10, 2020 to 28 in 2021, we made predictions with determined beta and kappa for the calendar weeks 29 to 45, for which data were already accessible to, of course, and thus a validation through trend observation and error computation became possible. And for the prediction, we used the standard ODE integrator, the non-standard finite difference scheme, and the long short-term memory, which I will also briefly explain next. So at first, I will give some exemplary parameter values in short. So here we are given the maximal number of infections we obtained with the NSFD approach, means non-standard finite difference scheme approach, using different beta and kappa values potentially corresponding to a certain variant, where here alpha stands for the alpha variant, delta for the delta variant, and O for the Omicron variant. These are, of course, exemplary values, but just to show you how much influence slight variations have from the outcome. So for alpha, we used small values and reached a peak of 210,000 infections per week. And for delta, we selected some higher values and attained 415,000 in the peak. And for Omicron, we finally had 720,000 per week. But it has to be clear that the data we use for prediction does not cover the Omicron wave, so we can hardly expect to get that high values in our final forecast, like 700,000, 800,000.
I'm a little confused now because
yes.
You said are these parameters beta and kappa, are they identified by pins?
Yeah, these are exemplary values because we found intervals with our pin in which the beta and kappa would lie then. And these are just the exemplary values to show you how much influence the different variants might have.
What does it mean exemplary? You mean in fragments of time or segments of time, you have different values of beta and kappa. That's what you mean?
Yeah, of course. For example, regarding the different waves, yeah.
Okay, and how did you, because we've done also similar work, but with a less sophisticated, and I know there's lots of parameters. We use the values from CDC from most of these parameters, but because here you only try to identify 2 parameters and you fix the other ones. How did you choose them? Did you have some guidance from like what do we have here, the CDC, the Center for Disease Control, or how do you come up with these other values of parameters?
We computed them from data, for example, yeah, the vaccination rate or the proportion of people who get hospitalized or die can be found in data, and and beta and kappa could not be found in the data, or that's why we selected them to be identified with help of the pin.
Yeah, so just to jump in, the CDC in Germany is called Robert Koch Institute.
Yeah.
So they recommend values, Matthias? They recommend values, yes, or
they provide a huge amount of data, and some of the parameters are, I mean, they are known more or less.
Right, like the duration of the infection and so on. They
publish very much data, and they also always update it. very much, also in time and so on.
But
so,
I was wondering the following: how do you, because we had many more parameters actually and time dependent. So I was wondering, how do you choose? How do you select to have beta and kappa as your identifiable parameters? Did you do some sort of a priori identifiability analysis to say, okay, I have that much data, the system is identifiable when I break it down to these globally identifiable parameters, beta and kappa, or is it like more empirical selection?
I think we thought that if we have many parameters that are known from the data, then it's also good to use those values, and then we've got a more safe prediction of the rest of the parameters. And in our previous work, we sometimes estimated more than 2, for example, 5 or 6. But the models were also different, slightly different. And maybe not so many parameters were already known from the data. Yeah, that was a reason.
So the recipe behind is also to choose the right time window. I mean, when you know that a certain variant is dominating the infection. So you have to pick out the right time window, and then of course you have to think about which parameters you can just fix and which parameters you have to obtain by calibration process. I mean, this is some discussion, of course. This is not straightforward.
Yes. Thanks.
Okay. Okay, so then we use this pin to approximate the solution Kp of T, where Kp stands for the compartment sizes and P again for the model parameters. And moreover, we've got K hat standing for the reported data of compartment sizes. And we're initially given 87 points in time, as I kind of explained, because we use March until November of the next year. And the weights W and the parameters PT are optimized during the backpropagation process such that the pin fits the reported data in the end. This is what the pin does. So it tries to approximate the solution of the compartment size. In our case, we concentrated on the infected and the hospitalized compartment. So K1, K3 and K4. Okay. Good. As I said, our loss function includes a data error and a residual error. And the data error is the mean squared error between the pin output and the reported data for all regarded points in time. And the residual error is the mean squared error between the so-called time derivative of the neural network applied to the output and the ODE system applied to the current pin output. And the time derivative can be computed using the Python automatic differentiation package. It's called torch autograd. So yeah, and we
Hi Sarah.
Yeah,
this is Thomas from MTSU. Can the weighing factor be learned by PIN also maybe as a future work?
Yeah, this weighting factor might. So we actually fixed the weighting factor. We tried different ones and had a look what the effect was, and I will also show some examples later.
Okay.
It's optimizable. Yeah.
Okay.
So yeah, the loss function now consists of the sum of the data error and the residual error, and those two components can be weighted. And we did that using alpha. It's a hyperparameter trading between those two losses in the multi-objective. Yeah, it can be done in the multi-objective optimization as well. And thus we obtain one minimization problem per training iteration. We implemented our program in Python with the PyTorch deep learning package. We give two inputs to our physics-informed neural network. At first, the vector of those 87 points in time, and reported initial sizes of 6 compartments. This is especially then for the prediction part. And we used 6 hidden layers, where 3 were used for the trainable parameters and 3 for the initial compartment sizes. And we had 1 linear output layer for the compartment sizes and a rectified linear unit one for the parameters. And we used ReLU and Tangen's activation functions and had 20,000 training steps per pin. Yeah. Okay, now I will give a short introduction to those NSFD schemes. They are the numerical method. Apart from an ODE solver, we applied here and we made use of it in the validation and prediction part with the hidden identified parameters and also the fixed parameters we had, of course. Yeah, and the following H is the step size. And okay, and those non-standard finite difference schemes, they have their origin in a paper by Ronald Mickens, published in 1989. And a numerical scheme to approach a solution is a numerical scheme for first order differential equations is called an NSFD if the first order derivatives are approximated by generalized forward different methods, where phi of h is the denominator function, which has to be determined for this NSFD scheme. And yeah, there is another definition saying that nonlinear terms are approximated in a so-called non-local way, where this non-local approximation comes from the fact that the approximation of a given function f is not only given at one point xk, but by f of xk, but can depend on more points. Now, we are here given already the denominator function of our model. And I did not write down exactly how we derived this. We explained this in our previous paper on NSFDs as well. But if we add a actually neglectable natural death rate and a recruitment rate to the model, which are the same because we want the same inflow as outflow. And we abbreviate this by mu. Then we obtain a differential equation for the whole population, which is mu times 1 minus n of t. And this is solved by a certain n. And then we can write this differential equation for n of t in a discrete form, and we can derive the denominator function by comparing this equation to the discrete form of the solution of the differential equation for n. So this is just in short, but you can also read this in this previous paper if you're interested. And then we used this denominator function in our implementation. We can set up the NSFD scheme like that. at first we get this implicit form, and then we can transform this implicit form to a sequentially explicit NSFD form. And thus we have obtained a discrete model instead of the continuous one, and use this for the prediction. And the advantages of NSFD are firstly that it's positivity preserving, meaning that for all initial conditions x0 larger 0 and initial time t0 larger 0, we have got x larger 0 for all t, meaning the system produces only non-negative solutions for positive input. And secondly, it preserves the stability nature of the origin and equilibrium points. Now, the second other approach we used is the long short-term memory. We'll also explain this. We wanted, our aim was to get a purely data-driven method, because the numerical, like the NSFD is numerical, the PIN is data-driven, but also includes the system of ODEs and its loss function. And we just want to see what does a purely data-driven method. And we found in the literature that the long short-term memory is very suited for this. It's a special kind of recurrent neural network, which is capable of learning long-term dependencies. And the main problem of conventional recurrent neural networks is the difficulty of learning to preserve information over multiple time steps. And it's also known as the vanishing gradient problem, meaning that, for example, exponentially decreasing gradients in the network backpropagation, in which gradients are updated proportionally to the partial derivative of the loss function, are finally obtained, and this should be prevented. So yeah, it has also been shown that the prediction accuracy of the LSTM model increases with increased training data. And yeah, so we also use this one. Per training step, an input sequence passes through an LSTM layer. So this is one layer of this network, whose output consists of the so-called hidden and cell state, and is passed to a linear layer then, and we select 100 neurons for the hidden layer. And one LSTM layer consists of an input gate, deciding which data are updated, a forget gate, determining which previous layer is discarded and which one remains in the current state. So gates are used to learn the significance of certain inputs. And the output gate decides which parts of the cell state are updated. N is the number of input features, D is the number of entries of the hidden unit, and XT is an input feature, W, K is a weight, BK is a bias, and the cell state or cell memory is known as the so-called long-term memory capability. And the hidden state is finally the output. It's computed using this cell memory, and it encodes the most recent time step then. So just in short, an introduction to LSTM. Yeah, you can find very good pictures of an LSTM model and its layers in the literature. Technically, the number of infected and or hospitalized, the number of people in the infected or hospitalized compartment in the following 18 weeks was predicted based on the numbers of the first 69 weeks that were used to train the model in the validation part. Actually we used two different two programs which were kind of the same, but in one of them we computed the data error concerning the hospitalized compartment, and we wanted to make a prediction of the hospitalization numbers. And then the other one, we used the data error for the infected compartment and wanted to get a prediction of the infected compartment size. As I said,
Sarah, can I ask a question? So in all cases, here it depends on from one state to the other, actually, how they do it. But you assume you have data for infections, right? You have also hospitalization, and you also have death, right? Mm. These are the three groups of data you have, 3 sets of data.
Yeah, we also have, of course, of the susceptibles and also vaccination numbers. Yeah.
Oh, you have a vaccination. I see. So the vaccination is also available, publicly available.
Yes.
Okay. All right. That's, yeah. Because we only had, it depends on the state, we had 2 or 3 data sets, I, D, and H sometimes.
Okay.
Yeah.
Okay. So, we ran those programs several times and got resulting beta and kappa in interval between 0 and 1. And we then computed that kappa and beta would most certainly lie in the following intervals. So those were selected as the final parameter intervals for the validation and prediction step. Then we selected those parameters within those intervals for the predictions or validations. We then tried certain values within those intervals, and I will show some examples at next. Yeah. Okay. I mean, these are very small intervals. Now, then this figure displays the trends of the errors, MSEU, which is the data error, and MSEF, which is the residual error, with alpha equaling 1/2 in 1,000 observed training iterations of PIN for parameter identification. As I said, this alpha influences the loss function in a way, and
why the loss function is so big? You don't normalize your data? 10 to the 10, that's never seen such a big loss function.
Yeah, we were especially interested in the decrease of it.
Yeah, but normalizing the data is there's values for that, for training, not just the numbers.
No, I think we didn't do that, did we? No.
So you don't subtract the standard deviation, divide the mean divide by standard deviation. You don't do the standard normalization. Okay.
No, we didn't do that in that case.
Okay.
I was also quite new to the topic of those pins because I only used numerical methods, and I worked into those neural networks at the first time, and so I did not normalize it actually, I think. At least, we got a decrease in the data error by more than 90% between the first and 604th iteration. And then it remained on that level. You can see there, and the residual error kind of increased, but the total training loss decreased from, in that case, 5.8 to 2.2, which is a reduction of 62% within those 640 steps. And all in all, we noticed a clear reduction of the loss curve, which we actually wanted. So yeah, it was it. Okay, now yeah, just one more explanation concerning the validation process. We used the data of the calendar weeks 10 to 28 of the next phase, I said. Then we used the beta and kappa values in the intervals obtained with the PIN, and then applied those three methods I mentioned to generate scenarios for autumn 2021. We focused on a specificity analysis and computing the difference between the reported data and the method-dependent predictions of infection or hospitalization rates. And we made some trend observance and mean squared error calculation as validation. And the LSTM structure was adapted often by trial, meaning the number of neurons in the hidden LSTM layer was adapted and the number of predicted time steps also. We did not perform a real sensitivity analysis, at least we have not yet. I did that very deeply in my master thesis, so I had a look of at the effect of parameter changes, how a parameter change affects the final curve. So for example, if we change the transmission risk or the contact rate or the quarantine rate, to have a look at the influence.
Can I ask a quick question? This is Yingjie from Brown. So in your previous figure, what training method did you use for that?
For what? For what?
What training method? Like ADAM or
ADAM.
Or LBSGS?
No, ADAM.
And can you tell me what, do you remember, what learning rate did you choose for that?
No, I don't remember, to be honest. We'd have to look at it. Oh. Okay, so.
Okay, thank you.
Okay. Now this is one exemplary prediction of the LSTM. You can see here in blue reported data curve, and in orange one LSTM prediction based on data of the first 69 weeks. So you have to remember that this method is really only data based. It does not get the system of ordinary differential equations. And it's of course on a higher niveau to those 18 weeks. We do not give a fixed starting data set to it as well. It meets the local peaks quite exactly, and the upward trend is also correct. And of course, per LSTM model run, the resulting curve looked very slightly different, and all outputs exhibited a much, not all outputs exhibited that much higher level, but generally we obtained outputs that always showed the correct tendency and captured outliers and peaks quite well. So we can also, okay. So therefore we use those beta and kappa you can see on top.
Can I ask a quick question on this figure that you have? This is Asan from Brown. So what is your training window here for the LSTM that you have?
It was,
I believe it's like from time/weeks 0 to 60, maybe 7, something that you have, where the orange curve starts.
Yeah, we used the data of all those 69 weeks, but the train window, I would also have to look it up. I think it was
okay, so I'm wondering why there is sort of like a discontinuity or like a jump at the very end of your training window, like at time 66 maybe, and the start point of the LSTM prediction that you have. So it seems that the training maybe was not properly done. so that the end of your training window was not captured correctly by the LSTM. And then in the prediction, you have at the very beginning a huge jump.
Yeah, we did not give that initial data set to this exactly as a starting data set to the program. Yeah, maybe we can still improve that, but yeah, I don't know.
Okay, thanks.
I think what Ehrhardt is saying is, this is the real data, but where is your LSTM result during training? Is it on top of the blue? Because clearly there's at week 69 there's a jump. There shouldn't be a jump. If the training was right, you should start from basically the same point.
Yeah, maybe we have to improve this still.
But Ehrhardt, who spoke, did a lot of runs like that for different states, and I don't think LSTM could work. There's no magic. If you have some sort of periodicity and so on, LSTM would work, and we've used it. But in this erratic behavior that we have in the COVID-19, I haven't seen any legitimate LSTM working. I don't know what your experience is, but here shows that it doesn't work actually.
Okay. I don't know.
I just remember that we did not force a continuity at this point, 69 or 68. I think this is what Sarah wanted to say.
Yeah, we wanted to compare this method to the other methods, you know, those other numerical methods here, you can see them below in green and red, and we see that they are more like smooth and stepless, and they also approach the upward trend quite well. They are, of course, they do not capture oscillations or small local peaks that well, as we can see, because they leave out the peak in the 78th week. And this is what the LSTM actually meets quite well. So, and also meets the final point very well. So we just had this as this comparison.
Well, can I add a comment? So basically, you don't need to apply any continuity in the LSTM. So for LSTM, it's sort of like a marching scheme when you do the prediction. So it starts from the very last step of your training and then starts marching in the forecasting part. Mm-hmm. And if you don't have a good end of training, then of course you do not start from a good prediction. Okay. And then everything may go wrong. But of course you still get the trend. It's an upward trend with some oscillation that you can also observe in the real data, the blue line. But I believe, I don't think that it's a fair comparison here that you have with the LSTM result and the other curves that you have, because I believe LSTM is not, either it's not trained very well, or there is something probably needs to be more tuned for the LSTM.
Yeah, maybe we have to kind of improve this. Yeah. Okay.
Yeah, I mean, we are not that experienced in this topic.
No, I'm not at all experienced. I worked into neural networks at the first time, so.
But yes, if you are interested, actually, DeepONet that we have, DeepONet can mimic LSTM without the expense, and DeepONet needs only 10 times less data than LSTM. So we have documented that in various time series forecasting problems. So, yeah. But LSTM definitely is not the right. I mean, it's used. It's the gold standard in time series, but you can do much better in 2022. We can do much better.
Could you send us some reference?
The DeepONet. You know our work on DeepONet, which is the operator regression.
Ah, okay.
So DeepONet can do it, can do this type of history forecasting.
I would also be happy if you want to loop in offline. I can give you some hints on either the LSTM or the DeepONet or pins for these models. I've been working on this a lot last year.
Yeah, Xan is the main author of our paper in Nature Computational Science that we published a few months ago.
Okay. That would be nice. Thanks.
Yeah, thank you. Okay, so then for the prediction, we also applied the pin, not only the numerical methods as we did before, and we gave some starting data to it. And this refers to November 2021. At this point of time, around 2/3 of the German population was twice vaccinated. And then we had a look at the influence of that alpha parameter in the loss function. So I also did not normalize there, just as the information. We selected alpha equaling 1/2 or 7/10 or 3/10, and had a look at 2,500 training iterations at first. And we found that with alpha larger than 1/2, of course, this is of course clear that the data error has more impact than in the other case. If it's smaller than 1/2, the residual error has more influence. And yeah, okay, so you've got here the one with 1/2, then here with 7/10, and here with 3/10, and we see that in the last case the loss curve finally reaches also the lowest level. Yeah, so the data error attains the smallest level for the largest alpha, and the residual error for the smallest alpha, and smaller alpha led to a flatter loss curve and a larger alpha to a steeper one. And yeah, so we found that the residual error, the inclusion of the residual error seemed very reasonable in the pin, because we also obtained the smallest final value of loss then. So this is what is actually wanted. Yeah. I think that was quite clear. Okay, so now what can be seen and analyzed here are infection numbers predicted by the pin in orange, LSTM in blue, and the non-standard finite difference scheme in green, and the ODE solver in red for the calendar weeks 29 to 46. And yeah, this is at first for the scenario alpha equaling 1/2. We've got other ones with different alpha values. So of course, if you think the LSTM is not good, then you can try to shape it out a bit, of course, because yeah, also in every program run, we obtain slightly different curves. They do not depend on this alpha. Instead, the pin prediction depends on this alpha parameter. And yeah, we gave fixed initial data sets to the numerical method. So they really start at the point, at the data points where the reported data start as well, or lie. Okay, so we notice that the NSFD curve increases weaker than the red one here, and reaches an almost constant level when the red curve already decreases after reaching a maximal value of around 245,000 infections per week. And yeah, those numerically generated curves are the same in the 3 plots because we use the same fixed data and the optimized beta and kappa here. Concerning this pin output, we note that smaller alpha leads to sharper local extrema, but not necessarily to higher peaks. So we had, in this case here, slightly more than 200,000 for alpha is 1/2. And here we have got a bit lower peaks. And here we had with the smallest alpha very high peaks of 340 and 180,000. Yeah, the pin and the LSTM also display similar decreases in terms of the point in time when the decline starts, which is around the 9th observed week. And the local minimum is less than 10,000 in this case here, and it's however, yeah, okay, if you if you have a look at the pin, then we find a minimal value of around 13,000. Yeah. Yeah, this is okay. The decrease starts around the 9th week. Also.
Sarah, how many slides you still have, because we're running out of time?
Yeah. Okay, so yeah, I can stop here now.
Okay, sorry.
Okay. Yeah, I can directly get to the conclusion. So yeah, concluding, the pin was used for parameter identification and its performance was validated by observance and improvement of loss curves, and loss curves exhibited different slopes depending on the weighting factor, which can of course be optimized as you asked. This but noticeably smaller value was achieved with smaller alpha, while the data error had less impact and the residual error had more impact. And we found smaller alpha in the pin loss function produced sharper peaks in the prediction part. And yeah, we validated via those trend observation and error computation. Yeah, and we also found actually that the LSTM had around 3 times as large error as the numerical methods, which was especially reasoned by that gap in the beginning. Yeah, because in other ways it reached those peaks well. So then all 4 approaches were used for scenario creation. And yeah, the NSFD did not capture those quite sharp outliers, which the LSTM method did. And yeah, it kind of sees those outliers and peaks. And yes, I said that NSFD and ODE solver used the correct initial data by precondition and yielded stepless and smooth curves with correct upward trends. And this is also what we found before in our previous papers. The pin showed a maximum at the end of 2021, in mid-January 2022, and also a slightly increasing trend from mid-February 2022 then. And yeah, the NSFD revealed maximal values, but no sharp peaks in mid-January 2022. Local minima were achieved in mid-February by the pin, and the NSFD still showed a very, very slightly rising trend then, and the ODE integrator displayed very slightly decreasing trend here already, because its peak was very slightly before that. And now we have got some references here. So these were the related approaches we had a look at. So 1, 2, 3 also worked on this deep learning of COVID-19 using pins, and number 4 and 5 dealt with the epidemiologic disease, disease-induced neural networks, for example, or epidemiology-induced neural networks, and those are the other references where also the data can be found of the Robert Koch Institute and the vaccination dashboard. And okay, that was actually my presentation here.
Thank you very much, Sarah. Thomas Torko actually is in the audience. Here we have a group.
Yes.
I think his advisor also. You reference his work.
Yes.
Thomas, congratulations! You made it to Sarah's list.
Thank you.
Thomas, you made it finally. But also you asked about optimizing the weights and the loss function.
Yes.
And I mean, we have very recent results, and Sarah has prepared one slide.
Okay.
Sarah, can you show this one slide? I mean,
yes.
it's a preliminary work, but we will publish this in a few weeks.
Okay.
So it's about not just, I mean, it's about systematically determining the optimal weights. I mean, really by multi-objective optimization.
Okay.
Yeah, and we are collaborating with guys from optimization, so specialists. Maybe Sarah, can you make it larger?
What do you say? Sorry.
Can you increase it, the picture?
Okay, yeah, of course.
Yeah, and I mean, today I had a discussion with people from optimization, and so you see on the right-hand side this Pareto front, which is a typical what you are investigating in optimization, with these two weights on the two axes, and you see it's a beautiful convex Pareto front. So it's for the guys from optimization, they told me it's the simplest case they have seen. Yeah. So usually it's more difficult. Yeah. I mean, this is a very good sign. So for people from optimization, this is an easy task.
Okay.
Yeah.
Thank you.
And we are working on this, and I think Sarah and another student, and we will publish this in the near future.
Okay. Thank you. Thank you, Professor George.
And I want to say hi to Stephen Moore. I also saw him. He's attending from Africa, right?
Yes.
Wow.
Yeah, we're international here. That's very international. Any questions for Sarah?
Yeah, hello. I might have one. Hello, I'm Sascha Ranfel from TU Graz in Austria. Can you hear me?
Yes, Sascha. Yeah. Hi.
Hello. So thank you. Nice talk. I was maybe I missed this. Maybe this is a silly question, but can you not train the LSTM with an additional regularization with a physics loss term?
Yeah, I think
kind of a physics informed LSTM.
Possible. This might be possible. Yeah, but we already used this pin for that. I mean, including this residual loss. So actually, the goal was to have a completely data-driven method to just have a look what this does. And so we did not include a physics term, but this should actually be possible, I guess. Maybe that.
What are you thinking about, Sascha?
So what I understood is that you tried it with a pin, and you tried it with this LSTM, recurrent neural network. But I was thinking, when you train a recurrent neural network, LSTM, you could also regularize that training with an additional physics loss term in the loss function. Or am I mistaken here?
I can add a comment here. So basically, LSTM works on the discrete data. And if you want to add physics to it, like say, for example, you want to add the ODE that you have for the COVID model, then you have to resort to other numerical methods, like, for example, finite difference, to add the equation into LSTM because it works on discrete data. But for pins, because you have a continuous representation of the function and you can use the automatic differentiation, then you don't have to resort to other numerical methods such as finite difference. And again, you are bound in your accuracy of your numerical method to the time difference, to the delta t of your time series that you have in your data. If it is huge, you cannot do any better than that because you are bound with the delta t of the data. That makes it a little bit hard to add physics to sort of like LSTM.
Okay, thank you. So it's not so trivial as I thought. Thank you very much.
Yeah.
Sure.
Do we have more questions for Zara? So we move to our second talk. Our second speaker is Dr. Yingjie Liu. He would be talking about the neural networks with inputs based on domain of dependence and a convergence sequence for solving conservational laws. A little bit about him. He has joined the School of Mathematics at the Georgia Institute of Technology in 2002 and is now a professor there. He was a postdoc in the Department of Applied Math and Statistics at SENU at Stony Brook between 1999 and 2002. He got his PhD degree from the University of Chicago and his bachelor's and master's degree from Peking University. His research interests include numerical analysis and scientific computing algorithm, partial differential equations, and machine learning. He has been working on moving mesh finite element method, conservation of front tracking, PDE identifications, etc. And more recently, he has been combining neural networks with numerical methods for solving differential equations. With that, I leave the floor to Dr. Liu.
Thank you, Samdata. Also, thank you, George, for inviting me. Let me share the screen. So, can you see the screen clearly?
Yes.
Okay. Good. So, I'm going to talk about our recent work on neural networks for solving conservation laws, and in particular, how to deal with discontinuities in the solution of a PDE. So this talk is a joint work. It's based on the joint work with my collaborators Haoxiang Huang and Vigor Yang from Georgia Tech. And if you're interested, now you can look for more details from the archive preprint, which is written down here. So let me briefly mention some prior art. There are a lot of recently, there are a lot of works, using neural network methods to solve, for example, hyperbolic equations, fluids, and PDE in general. So, for example, the physics involved neural network by Resi, Perdicaris, and Kaniadakis in 2019 use this incorporate the PDE into the loss function. And this is a very, very convenient method. You don't have to be very detailed in the coding. You can essentially do a grid-free method, incorporating various physical properties into the neural network framework. The other approaches, for example, using an expansion of neural networks to map from, let's say, a solution patch to the solution at a future location. And this can be used, to predict, very complicated nonlinear functions. And there are also approaches using neural network to improve existing schemes. For example, you can use the neural network to predict a limiting factor, a limiting parameter, or use the neural network to determine the size of the artificial viscosity. And this will help improving an existing scheme for shock capturing. So for example, this works by Abgrove and Vega, Dicasiati, Histovan, and Ray in 2020. The more closely related work to today's talk is using the neural network to map a low-cost solution patch to a high-fidelity solution patch. And this work, for example, done by Liu Wang in 2019 and Ran and Tai in 2021. The idea of this approach is that you try to save, you try to reduce the complexity, and try to recycle, let's say, the numerical solution from a low-cost numerical scheme, and use that to predict, the high-fidelity solution. So our work, today's talk, is closely related to this approach. So we try to predict a high-fidelity solution at a space-time location, let's say xt. And let's say the model equation is a conservation law. And well, in order to predict the solution at this location, we need to figure out, the domain of dependence, right? Because there is you need to figure out, what kind of information you need to predict the solution at this point. And for conservation law, we know the information is traveling at finite speed, limited by the largest characteristic speed. So if you look at the space-time location here, you can draw, two lines in the xt plane determined by the largest characteristic speed, and this will give you a domain of dependence. If you know the information in this domain of dependence, and supposedly you are able to determine the solution at this point. In particular, in order to make the math more efficient, we want to use a local domain of dependence, in this colored area. So we want to take advantage of the low-cost numerical solution in this local domain of dependence and use them to determine the solution, high-fidelity solution, at a single point, at a single space-time location. Okay, so now suppose you have a low-cost scheme to predict the high-fidelity solution. Sorry, you have a low-cost scheme, let's say on this grid, space-time grid, and you suppose you know the solution at this space-time location, this one, and this one. So this forms a local space-time domain of dependence for determining the solution value at this point. So the question is, can we use a low-cost numerical solution at these 4 space-time locations with the help of a neural network to determine the high-fidelity solution at this single location? Well, if this numerical solutions, put into the input, let's say, accurate enough, of course, this is true. But, in order to reduce the complexity, in order to make the math efficient, the low-cost math usually is it's very low quality, and it's very smeared solution. Let's see what happened.
Yingjie, can I ask a question here?
Yes.
Because it seems to me it would be more useful if, because now you're in a lattice, but I'm thinking of a semi-Lagrangian scheme where you can actually track back the characteristics. So that would be very useful for semi-Lagrangian schemes too, right?
Yes. So it doesn't matter what scheme you use.
Suppose, so you don't have to land on the node of a lattice. It can be, right? You know what I'm talking about, right?
Yes,
yeah, exactly.
Yes, it doesn't have to on lattice. You're right. It's just just like here, just figure out the solution in this domain of dependence. Yeah. So let's say you have a numerical scheme which is grid-based. So let's say you have this point, and the question is, can you use the solution at these 4 points, a low-cost solution at these 4 points, to predict a high-fidelity solution at this single point? Now let's look at the case of a shock wave. Say you want to predict a solution, let's say, which is a shock wave, and the solution you want to predict is located here. And the input, because it's based on a low-cost numerical solution, so you use a low-cost solution to simulate this shock wave, you get something like this. So this is going to be used as the input because it's computed by a low-cost solution. Low-cost numerical scheme, sorry. Now let's say if you change the subject, you want to predict a smooth way like this, and you apply the same method. So you use a low-cost numerical scheme to simulate this smooth way, and this is what you have. And you can see, this smooth way is predicted pretty well by a low-cost scheme. And you want to put this into the input of a neural network to predict a solution for this smooth way. Now there is a problem here. So the neural network look at this input, the input from a low-cost solution for the shark, the input based on the low-cost solution for a smooth way. And the neural network cannot tell any difference between them. They look almost the same. This is very typical, because when you use a low-cost numerical scheme to approximate a shark, you will get a very smeared solution. And the very smeared solution, by looking at it, has no difference from a numerical approximation of a smooth way, having a large slope. So if the neural network is not able to distinguish between the two low-cost solutions, how is it going to be able to predict the solution for shark and for the smooth way? You cannot even distinguish the two ways. So if you use the low-cost solution simply based on the domain of dependence here, it's not going to be sufficient for the neural network to predict a solution. It's not sufficient. Let's look at another approach. Say the solution, the subject you're studying is a discontinuous solution, like a shark, contact discontinuity, etc. Now let's say we approximate this discontinuous solution by, let's say, a convergent sequence of numerical solutions. So let's say you approximate it by a numerical scheme with mesh size h. You get something like this. Well, it's smeared, very smeared. And if you refine the mesh, let's say h/2, well, you will see the numerical solution. If it's a converging numerical solution, it will get better. It looks better. I mean, it looks closer, to this discontinuity. And if you keep refining the mesh, let's say h/4, you will see the numerical solution begins to getting steeper and steeper near the discontinuity. So this is a very typical behavior of a convergent sequence of numerical solutions. So during the converging process, you will see the numerical solution getting steeper and steeper in approximation of a discontinuity. Now let's look at another subject. Let's say this smooth way. So we want to approximate this smooth way by a convergent sequence of numerical solutions. So let's say the numerical solution is computed with mesh size h. Well, you can see the numerical solution kind of mimic the smooth way. And if you refine the mesh, well, you will see more points. But the profile doesn't change very much because the solution is smooth way. And you keep refining the mesh. Let's say h/4, you have more dots, even more dots. But the profile is still the same because it's a smooth way. So the conclusion is, as you refine the mesh, or in other convergent sequence of numerical schemes, there is a big difference between a discontinuity and a smooth way. To approximate a discontinuity, the numerical solution in the convergent sequence is going to get steeper and steeper. On the other hand, in approximating a smooth way, a convergent sequence of numerical solutions does not behave like this. It will essentially keep its form. It doesn't get steeper and steeper. So from this dramatic difference of approximating property by numerical solutions, we can use them to help the neural network to distinguish a discontinuity from a very steep smooth way. So that's our basic motivation. Now we're going to design a two-coarse grid neural network. So we still try to solve this. We still try to solve this conservation law. Let's say we solve it with a numerical scheme, but we equip the numerical scheme with two types of meshes. One is with delta x and delta t, that's the grid size. And then we obtain the solution. Let's say u, I, n, I have a prime here, which means that solved with grid size 1. And we solve the equation again with the same scheme, but we refine the mesh. Let's say half delta x and half delta t. And we obtain another set of numerical solution. Let's say u, I double prime, n double prime. So this double prime means that it's solved with another grid, a refined grid. So let's label this numerical solution in the two grids. So on the coarse grid, you have a solution like this. This forms domain of dependence. On the refined mesh, you also specify the 3 locations corresponding to the previous 3 locations. Right? They're staggered because the mesh is refined. So we locate the same locations, we find the same locations, and pick up the solutions computed with the same scheme on the refined mesh. So now we have six numerical solution values to be used for the input. One is from the mesh size delta x, delta t. One is from half delta x and half delta t. So this is the one from the original mesh, and this is the one from a refined mesh. They correspond to the same location, space-time location, right? So we line them up and put them together, and this will form our input. So from this input, we expect the neural network to distinguish the discontinuity from a smooth way. And the output.
Yingjie, I missed something here.
Oh,
I mean, I understand everything so far, but did you talk about the neural network, or are you going to talk about the neural network now?
So far, I'm talking about input. That's I'm going to the input. Yeah, I haven't talked about neural network yet. I will get to it in a minute.
Because you call it 2CG and N, so
Oh, okay.
Where is the NN?
But neural network is just the old-fashioned neural network. I mean,
okay, old-fashioned.
there's nothing special here.
Hopefully more than one layer.
Oh, okay. Yeah. So neural network it's the very commonly used one. So the only difference is the input. The only novelty we have made is the input. We have done nothing to the neural network. Yeah. So the input consists of 2 numerical solutions, one computed from the original mesh and one computed from a refined mesh. And the output of the neural network will be the solution at a single point. That is the solution at this point, or equivalent at this point. They refer to the same space-time location. So you have, let's say, 8 elements in the input and 1 element in the output. All right, let me talk about the neural network. So there's nothing we have done to the neural network. It's the same one. We use a commercial one, the TensorFlow, and we use the free version, the TensorFlow, and we run this TensorFlow in the cloud. So thanks to Google. So all our computation is done by TensorFlow, which is very, at least for our application, it's very easy to do. Runs usually, no more than a day. So for predicting solutions of 1D Euler system, for Euler system we have density, velocity, and energy, these variables. So we will use 8 hidden layers, and each hidden layer contains approximately 300 neurons. Why 300? Because you have 3 variables: density, pressure, and velocity. So for each variable, it is we have to allocate about 100 neurons. So it will be 8 times 300. That's the neural network. And because this neural network is very local, I will mention later. So actually, it's very easy to train, and the data required for it is I would say minimal. So what's the training data? Well, for our simulation, we simply perturb the Riemann problem. So if we want to predict a Riemann problem, we just perturb the initial value. Let's say plus minus 2%, plus minus 4%, 6%, 8%, 10%, and use this perturb the initial value to compute. Well, use a reference code, of course, to compute for the exact solution. And use this exact solution. Well, it's not exact, but it's a high resolution solution. And use this high resolution solution as a reference solution to train the neural network. And once the neural network is trained with this data, probably I would say it's minimum because it's not much, just perturb it. And we use the data, most of the data at the final time to train. And then we use this data to predict the solution that's the original problem. So that means we has no 0% perturbation for the initial data. Or we can perturb the initial data by plus or minus 3%, plus or minus 5%. So this even number, even percentage perturbation is for training, and this odd, well, including 0%, is for prediction. Right? So
sorry, this is Lulu from Japan. I have one question here. How do you perturb exactly? So you add a Gaussian noise, pointwise, or you have Gaussian field?
No. It's very simple. We just, let's say, perturb the initial data uniformly 2%. So let's say I multiply the initial data by 1.02. That's what I call perturbed by 2% everywhere.
Okay, I see. Okay.
Yeah. So there's no, well, because we really need very little training. I mean, this is a local neural network, so the training is really easy. Well, maybe in the future when problem gets more complicated, we need to probably do a random type of perturbation. I mean, but currently, the problem is so easy. The neural network is so small. It's basically a local neural network. So the training is requires very little data, a uniform training. That will be enough for our problem. And let me explain how to compute the inputs. So we use very coarse mesh. So we use 50 grid cells for the original mesh, and then we refine it. So then it becomes 100 cells. That the 2 grids will be used to compute the inputs, and these are 2 coarse grids. Right? The reference solution is computed by a high resolution finite volume scheme on 200 cells, and the scheme is based on hierarchical reconstruction limiting and using partial neighboring cells. And this work is by me, Xu, Tadmore, and Zhang in 2007, and Xu, me, and Xu in 2009. So this is the scheme for use. We use to compute the so-called exact solution, which will be used in training and which will be used, as a comparison for the prediction. I would like to mention that for the reference solution or for training the exact solution, you don't have to use this scheme. You can use any other method, high resolution method, to compute for exact solution for training. All right. So let's mention the scheme for use for computing the input. We use very simple schemes for computing input. We use first order schemes. So what's the simplest first order scheme? Well, the Rusanov scheme is a very simple scheme. It's first order. So we just write this discretize the solution, time derivative, and the flux derivative. And this fluxes, you can use the so-called Lux-Bridges flux. That's the feature of the resonative scheme. So this is a conservative scheme, but it's first order actually. Very easy to code, very efficient. And use this simple scheme to compute on two grids. One is the original one is the refined one. So we obtain this result. So let's first look at the input. If you plot inputs, you can see the light blue one is the one with using the first order scheme on the original grid, which has 50 cells. And this red one is the same first order scheme computed on 100 cells. So it's very diffusive. We use these two diffusive solutions as input and feed into the neural network, which is the TensorFlow, with 8 hidden layers and 300 neurons on each layer. And the predicted solution is the dark blue. And it's very sharp, very sharp. So it has very minimum points in the transition, in the discontinuity. I would guess if our reference solution is more is sharper, then the neural network prediction can be further improved. But but I think this is already good enough. So this is for density, and this is for the pressure. You can see the dark blue predicts the pressure pretty well, and the light blue and red are the two input solutions. They are very diffusive.
Yingjie, can you? I think again I missed. Maybe Lulu. I don't know if anybody understands. How do you actually train the neural network? This is supervised learning, right?
This is the simple way. The simplest loss function. So we just define the loss function to be the error between the prediction and the exact solution. So it will be the sum of the square of the error between the prediction and the exact solution. Kind of like you are training for for image detection, something like that. It's the most commonly used loss function. Sorry. So let's for example, the neural network with this input and output will be 1 point value, right? And then the loss function will be this 1 point value minus the exact solution you use in training. And then you add this error together, and this will be the loss function.
How do you know the exact solution?
Yes, so this is the exact solution is computed by, let's say, a high resolution scheme.
But then what's the point?
So we use the high resolution scheme, to train the data on, let's say, on certain examples, and then we try to use the trained neural network to predict the solution. It's like interpolation on all variations.
So are you changing the initial conditions, or is still the lax problem?
Yes. It's still the lax problem, but I change the initial data.
So what does that mean? That, for example, if I have pressure on the left, pressure on the right, can I go from ratio of 5 to a ratio of 100?
Well, if the data you try to predict is too far away from the data you use in training, then it's not going to work. So for example, if you train the data with pressure 5, you train the data with pressure 10, you train the data with pressure 20, then I think, if you predict the solution at pressure, 6, 7, 8, 9, or whatever in between, they will be pretty accurate.
Okay. I get it. So it's basically interpolating initial conditions and make predictions faster after you train it. Yeah. Okay. Yeah. Sure. Of course, that's very useful. Yeah.
Yes. So basically, because the neural network is local, so that means you may be able to train it, with a limited amount of data, but you can apply this neural network to a much larger set of data. The reason is because if you look at a local patch, small patch of solution, there's not much difference. I mean, we hope, right? So it's basically interpolation. Yes.
Hello, this is Amaya from Brown.
Yes.
I have one question.
Yes.
So can you go to the figure which you plotted just now, which you have shown?
Yes.
Okay. So here, the blue and the red curve is the data which you are providing. That's a low fidelity data, right?
That's the input data.
And that's the input data. So basically, if you see the pressure and the velocity plot, you are actually giving the location of discontinuities. I mean, it is smeared. They are still smeared, right? But they know where is the discontinuity and where is the smooth.
Yes, yes. So you have a good point. So because you are inputting, two inputs in a convergent sequence, you somehow can think, oh, because they intersect, right? They intersect. So I believe the neural network take advantage of this information to help predict the location, the correct location of discontinuity.
Okay. So so if you provide the data a little bit earlier, I mean, okay, this is the data at the same time.
That's right. So the data, not at exactly the same time. So it's based on domain of dependence. So the data this is at the same time.
Okay.
And this one is just 1 delta t.
Slightly.
Slightly.
So if you go further below, I mean, towards the initial condition, what will happen? I mean,
well, you can certainly do that, but the neural network will become larger and larger.
Okay. Because from our experience, it was really difficult to capture this kind of shock waves with just the initial condition. And you are using a data inside the domain, basically.
Yes. So basically, I'm using local domain of dependence. That's the key here. I use the local domain of dependence.
But in general, this data is not available. Of course, you are finding it from the numerical solution.
Yes.
But in general, it is not available except the initial condition.
Yes. So this our approach is actually a combination of low-cost numerical scheme and the neural network. So we do not intend to use neural network alone to predict the solution. We assume you already have a low-cost solution to compute the solution, which is very low cost, and the neural network will be built upon this low-cost solution.
Okay.
Yeah. Thank you. Very, very good question.
I think Yingjie, we have and Boris here. In the weather prediction, people try to do something like that with they call it nudging. Nudging, that is a nudging term. This correction, and it's done through the neural network.
Could you explain a little bit
it's the same idea. They just call it differently, but actually they have only one grid and then observations or some. It's called nudging. So you sort of try to run like in climate because these are big computations. So you're trying to do like instead of 1 kilometer, you do 100 kilometer simulations, right? And then it's mostly advection like you have, but they don't have shocks, of course. But they're trying to learn that correction to add it to the coarse grain scheme that you have now. What you are doing here is because of the like you said, if you have discontinuity, you actually need 2 grids.
That's right.
Yeah, exactly. To see where it is. I think that's fair.
Okay. Thank you, George. So actually, there are works, besides the work George just mentioned. Let's say, let me go back to the reference list. So I already found 2 works. They use the local solution patch to predict high fidelity solution patch. I mean, for those of you interested. So our work is closely related to this work and also to the work George just mentioned. Yeah, we use the low-cost solution patch to predict high fidelity solution patch, and our so the key point we are doing here is we try to use a local patch to predict a solution at a single point, rather than from patch to patch. We use a local patch to predict single point. And this makes the neural network solver very local and therefore very easy to train.
Can I ask a quick question? This is Yingjie from Brown.
Yes.
In your training, I noticed that you add the noise in your input. Is that right?
No, I didn't add noise to the input. I just compute the numerical solution on two grids. One grid with match size H, one grid with size h/2. Yeah.
Can you show me again the slide where you explain the noise part?
You mean here? Oh, you mean here?
Yeah, there.
Oh,
so
this is not noise. This is not noise.
Perturbation.
I put a perturbation to artificially create some training data.
Ah, I see. That's only for initial data.
That's right. So I perturb this initial data, and then I use this high resolution code to run on this perturbed data to generate the exact solution for training.
I see. Got it.
And once the training is done, I hope the neural network can do the interpolation work and to predict, all other close enough data.
So I'm wondering, for this setup, I noticed that your training is 2, 4, 6, 8, 10, and your testing is somehow in between 3 and 5. So that have you tested on like 11%?
I don't think it's going to be very good. This will be extrapolation. Ideally,
right. Then what about, have you tried the 7 and 9? So I'm just wondering how this would be performed well in the unseen realm.
That's right. Good question. So I don't think there's any problem on 7 and 9 as long as it's covered by this data. There's no problem at all. Yeah, and I also believe we don't have to be so the training data doesn't have to be so close to the prediction data. I mean, this is just a first paper we have done, but this method is pretty, I would say, pretty robust.
I see.
As long as the data, go ahead.
Yeah, because I saw that you have a 0% perturbation, so that is extrapolation.
No. That means you train the data with 2% and a -2% of the initial data.
I see.
I'm predicting the solution with no perturbation of the initial data.
I see. Got it. Thank you so much.
Okay, you're welcome. So you can see the input solutions are very smeared because they're computed by first-order scheme, which is very efficient, but it's also very bad. But as long as it captures the the concavities, the prediction is very good. And we also do another prediction. This time we predict the solution with the initial data being a 5% perturbation of the original Lex prop. So we obtain the same result. Very good. So this 5% perturbation of the initial data corresponds to this one. So we predict at the 5%. This is not the original Lex prop. It's a 5% perturbation of the initial data to the Lex prop. With this training, and we can predict pretty well. And then we want to test on different type of numerical schemes for computing inputs besides the Rusonov scheme. So a very commonly used scheme is the so-called leapfrog scheme. Leapfrog scheme is so commonly used and so easy to implement. You just stagger, this time discretization from n+1 to n-1. You stack the spatial discretization from i+1 to i-1. However, it's unstable because of the diffusion term. So this is very well known. Actually, I couldn't find the reference for this, but I learned it when I was a graduate student. So this is well-known unstable scheme, but it's easy to stabilize it as long as you change the diffusion term from a discretization from n to time level n-1, then it's conditionally stable. All right, so it's a very simple scheme. We don't have to spend too much time on this one, but it's very easy to use. And use this one to compute inputs on two grids, one the original one the refined one. We obtain almost identical result. The prediction, very sharp, and the inputs are very smeared. Inputs are very smeared. The light blue and the red one. So no problem at all. And then we further modify the schemes for computing inputs. We know that this leapfrog scheme is unstable for diffusion, So can we, use another strategy? Let's do the operator splitting. So we do the advection part, convection part first, followed by the diffusion part second. So we split the scheme into 2 steps, then it will be stabilized. And we do use this on 2 grids to compute it. And it does the same. You can see, there are some overshoots for the input, but the prediction is perfect. Prediction has no jump at all, no problem at all. So despite this, despite the bad behavior of the input, it doesn't seem to affect the prediction. And then we use the resonative scheme on 2 different grids to compute input for another problem, the SAT problem. So, so you can see the prediction is pretty good. The input are very smeared. You cannot even tell what is real shock, real content. But based on this very smeared input, the prediction is pretty good. And this is the pressure, and this is the velocity. There's some overshoot for the input, but there's no problem at all for the prediction. And we use a different type of scheme for computing inputs for the SAT problem. This is the leapfrog and diffusion scheme, stabilized, and we have almost the same good result. Predictions are very sharp. The inputs are very smeared. And we also change the input scheme, to the leapfrog and diffusion splitting scheme, and we obtain essentially the same result. Very sharp prediction and very smeared input.
Excuse me, I have another question. So for the network, it can only predict for this specific time t equal to 0.158, or it can predict the entire domain.
It doesn't matter as long as you put input at the domain of dependence. So let's say it doesn't matter, depends on your input.
Yes. So yeah, but I'm still thinking whether this would be a fact, let's say the training or some learning of the difficulty of the network.
Oh, so during the training, because the neural network has no eyes, it only knows the input. So when you put the input, which has how many data? eight elements of data, and then it will give an output. And so if you put the input here, it will give the output here. If you give input some here, then it will give the output here.
But can I rephrase what Lulu is basically asking is,
yes,
let's say you have dispersion errors, or the shocker propagates at different speeds. The speed will depend. You don't have a conservative scale. The shock will propagate, or the expansion will propagate at different speeds at different resolution. So you have phase errors. How could you correct the phase errors?
The phase error.
So the time will not align. That's the problem. You see, right now you basically have diffusion.
Right.
But I'm talking about imagine you do long time integration. And
I understand what it means. So what you mean is that the numerical input, the smeared input may be slower than the real shock. Is that what you mean?
And not only that, the two resolutions will give you different locations.
That's right. So good question. So that's the limitation of this method. So this method will be very good in predicting the loss of amplitude. So if the loss of amplitude is large, this prediction will recover it with no problem. But if there's a large phase error, let's say the phase error is so large, it's already make the numerical shock out of the domain of dependence. Let's say the domain of dependence actually doesn't have a shock at all, in the low-cost solution. Then I don't think this method will work. So this method will, let's say you have two-cost solution. The two-cost solution should be close enough to your true solution before in order to make a good prediction. Yeah, it's not, this method is not let's say can solve all problems. Yeah. So you can see from this result, yes, the smeared solution is very smeared. I mean, the input is very smeared. But if the solution, input solution is, has a large phase error, I don't think it will work. Yeah. Did I answer your question, George?
Yeah, of course. Yeah. That makes sense. Yeah, that's what
there's a limitation, definitely.
Yeah, that's the problem with time dependence. That's what Lulu was asking, basically. How do you align the stars? That's
that's right. Yeah, if the phase error is so large, let's say in the numerical input, you don't see a shot and you want to predict a shot because the phase error, it's already more than 1 delta x, then it's impossible.
Yeah.
A very good question. Thank you. So we say. Okay, so now what if we don't use 2 grids? I mean, the idea is that we use a converging sequence in the input. So we don't have to use 2 grids. For example, we can use the vanishing viscosity approximation to the physical solution using one grid. So let's say we perturb the diffusion with delta x or with 4 delta x. And the 2 perturbation will naturally create a converging sequence. So we compute the 2 equations with the same numerical scheme. Let's say we obtain the solution capital U and capital V, right, on the same grid. Now we don't use two grid, only 2 diffusion coefficient. And then you can put the 2 numerical solution line it up from domain of dependence. And this one will be used as input. And the output will be the solution, a single solution at the point, at the tip of the pyramid, domain of dependence. In case of systems, let's say the Euler systems, this one will be multiplied by, let's say, 3 in 1D, multiplied by 4 in 4D, sorry, in 2D. I mean, so let's say you can write it as input density, input velocity, input pressure, and the output will be, density, velocity, pressure at the space-time location. By doing so, you can do the same thing. You can see the prediction is still pretty good. This is the dark blue is the prediction, and this red and light blue is the input. The inputs are pretty bad, but the prediction is very good. And we can easily extend this to multi-dimensions because there's almost no work to the neural network. It's just a slight modification of the input. So we extend this to, for example, a 2D Riemann problem. This is the configuration 6 in the paper by Peter Lex and Xidong Liu in 1998. So the Riemann problem look like this, and this actually is the prediction from the neural network. And let's examine the density. We're going to cut here, cut here, cut here, and cut here, and compare the density on this cutoff, the cross section, with the exact solution. Here it is. So this is the cutoff at y equal to 0.34. That's about the cutoff here. That's the cutoff here. And you see this light blue and red are the input solutions, pretty bad. And this dark blue and the green one is the exact solution. The dark blue is the prediction. Almost totally cover the green solution. And this is the cutoff, the cross section at y equal to 0.5. That's here. 0.5 is here. So we slice it here and examine the density. So you can see, the light blue and the red one, the input are pretty bad. The amplitude of the input miss a lot. But the prediction, the dark blue, is very good. It captures the green one very well. And this is the cutoff at y equal to 0.6. That's about here. Cutoff 0.6. And you can see the blue and the red, the input solutions are pretty bad. However, the dark blue, the predict solution by neural net, captures the green one very well. And this is y equal to 0.7 near the top. It does pretty well. This is a shock wave, very narrow shock wave. And this is at y equal to 0.8. that's about here. There's a single shock wave here. And this single shock wave is captured by the dark blue pretty well. And the input solutions are pretty smeared. Thank you very much for your attention.
Thank you very much, Yingjie. That was really interesting. So, for the smooth part of the solution, what would you do? Because you can have, the other problem that Qingwan and you guys are solving is, you have a shock and you have a density right before the shoe and Osher problem.
Yes.
Yeah. So the density fluctuations in that case, yeah, if you can resolve the shock and so on but now what happens to the smooth part?
Oh, okay, good question. I believe it has no problem to the smooth part, because if you can look at, for example, there are a lot of smooth parts here. Oops. Yeah, this is the smooth part of the solution.
Yeah,
I mean, it can capture the shock wave and other discontinuities, but as a side benefit, it captures the smooth part very well. That's a surprising part of this method. I mean, there's no problem for the smooth part at all. We have done other problems. I think the shoe washer problem will be easy for this method, because
that would be nice to see, actually, because I like that problem. Is not trivial at all.
Yeah. We haven't tried it, but I believe it's easy, because as you said before, it has no phase. Has no large phase error.
Yeah.
But amplitude error is very easy for this method.
Yes, it's good.
It recovers amplitude very well. Yeah.
Matthias has a comment. Matthias, maybe you can turn on your microphone and talk to Yingjie, and talk to the group.
Yeah, it's it's just a comment that came in my mind. So first, thank you for this very impressive talk.
Thank you.
I mean, we have worked on the same topic. So how to solve hyperbolic PDEs? I mean, non-linear PDEs. So with shocks and the reflection waves. I mean, we're also working with neural networks, but this is everything we have in common. I mean, in detail, our approach is quite different. We are just tuning existing state-of-the-art schemes, and we thought about the Wino 6 and Wino 6 scheme, which is somehow an established scheme. And I mean, the scheme is derived by Taylor expansions to check the. I mean, it's not the convergence, because it's a nonlinear problem, so you can only talk about accuracy. And of course, if there's a shock, then all of these stuff with Taylor expansions, they break down, so they are not valid anymore. And this is exactly the point where the neural network enters. So at the shock, all these derivations and accuracies are not valid, and you can train your network, and you can improve somehow or modify. You can modify the coefficients of the scheme, and this modified scheme has a better shock capturing than the original scheme. Yeah, and also the network is very small, so it has just I think only I don't know, 3 levels. So it's a very small network. So it's computationally very cheap, and we also discovered, I mean, just by experiments, that you can train it on a certain problem, on a certain, let's say, Riemann problem, and if you consider next time, let's say, a neighbored problem, not the same problem, but a similar problem, this training is still valid. So it can also deal with similar problems. So you don't have to train again and again. If the problem is in some, let's say, neighborhood, then it is also working.
Yeah, good. I think it's because of you're using the local data, right? It's a local prediction. Yeah, I think that's the benefit of doing this local neural network prediction. Yeah. Very nice.
Yeah.
Matthias, I was just looking at the paper. Actually, it's very interesting. How do you deal with the issue of dispersion that I mentioned? From the course, because I, when we were doing also the multi-fidelity, when I have really bad low fidelity models and I can, and a few points in high fidelity, I can predict it. We solved the problem with amplitudes, but it was really the issue of if you don't align, the phases are not, if you're out of phase, then basically you have to go to high dimension to do that. Yeah, right. So we found ways to do that, but it's really painful for arbitrary cases. So for me, it's not just only the amplitude; it's really also the phase.
Yeah. So we know it's a whole family, and it's still developing today. And there's one sub family. I mean, you are determining the coefficients of the Vino family.
Yeah.
And there's one subfamily that, I mean, it depends on the objective. And there's one subfamily that is called dispersion minimization, dispersion error minimizing.
Oh.
And
nice.
but we did not consider this type of subfamily. But there is a certain kind of these dispersion error minimizing Vino schemes, and we could apply our approach also to this kind of family.
But you can appreciate how much more difficult this is, right? Because chaos is basically a randomization of phase.
Yeah.
And we know how difficult it is to capture chaotic solutions.
Yeah, that's true.
Yeah.
Hello, Matthias. This is Ameya from Brown. I have one question. So basically, in your paper, I was looking at. So are you tuning the parameters of the smoothness indicator for Vino scheme?
Yeah, you can put it this way. These are so-called nonlinear weights.
Okay.
And they are somehow updated by a multiplicative perturbation.
Okay. Yeah. Thank you.
So the idea is strikingly simple, but it works.
So when you do the training, do you need to use a successful weight distribution to as a
yeah. So we are, I mean, as I said, we are still new to this machine learning community. We computed a reference solution on a very fine grid.
I see.
And we use this for training.
I see. So this one computed on the fine grid is based on a successful nonlinear way, right? A successful nonlinear way.
For the reference solution, we use the standard Vino 6 scheme.
I see.
But on a very fine grid.
Oh, I see.
You have to do it once.
Oh, I see.
Can I ask a quick question on your experiment? So
yes.
Can you tell me what is your network architecture and what activation function do you use for all the experiments? Thanks.
Oh, this is used. We use the online version, the free Google version, the TensorFlow. I believe the activation function is the common ReLU. We haven't done anything, to modify the neural network. It's the free version.
Okay, so I was asking that depth and width. But yeah, anyway, thanks.
Yeah, hi. Adar from Brown. I was wondering if you tried cascading your inferences to create like some sort of a time-dependent solver.
Could you say the question again?
So if you tried like making an inference to get like you showed a single time inference,
right.
And taking that and maybe subsampling it and trying to push it again to the same network to get the further time step, kind of like what leapfrogging does, but with your super resolution method.
Oh, I see what you mean. It's completely doable. Yes, completely doable. Let's say you update the solution at time level t equal to 1, right? You can use the updated solution, let's say as initial value, and use your low cost scheme to compute this exact solution at 2 grids, and to until you get the time t equal to 2, and at time t equal to 2, and then you can use this neural network to predict again. Yeah, that's totally doable. Actually, one of my students is working on it. Hopefully, this will help you, extend the solution for a very long time, without much loss of the amplitude.
Yeah, I'm saying because we had a similar work, and for us at the initial step, the network was predicting very well, and we managed to produce graphs like yours. But when we tried this cascade, it failed. So this, and we had to find a way to actually make it work after cascading. So this is an interesting issue to check. That's why.
Yeah, I understand what you mean. So it all depends on the training. Yeah, very good. So let's say if you do the training, let's say from t equal to 0 to t equal to 1, and the training may not work at t equal to 2. That's what I'm thinking. So yeah, but if you have a local neural network, yeah, I think it's possible to cover the training more easily. You understand what I mean? So you can you can you can afford to allow this this data the training data to be a bigger block. Hopefully it will cover cover your prediction at future times, much beyond time equal to 1, time equal to 2, and time equal to 3, etc. Yeah,
exactly.
So yeah, it's all based on the training data, the availability of training data, I think.
Yeah, thank you.
Yeah, you're welcome.
Thank you, Dr. Yingjie. Do we have more questions for him? So if we don't have any questions, let's thank both our speakers for the wonderful talks that we had today. With that, we come to an end to our seminar for this week. And everyone have a very happy and a safe weekend.